In an era of dwindling subterranean riches, modern engineering has turned its gaze toward the planet's greatest reservoir, the oceans. Here, where crushing hydraulic force meets the precision of molecular chemistry, begins the story of transforming liquid into the hardest metals known to man. We don't just see salt water, we see a liquid mine containing nearly every element on the periodic table. The challenge isn't existence, but extraction. Iron, the very metal that built our civilization, swims here in a hidden ionic form, waiting for someone to seize it. The process begins with concrete and steel behemoths anchored to the seafloor. These massive intake pipes are forged to withstand staggering atmospheric pressure, serving as the primary arteries that feed the factory's beating heart with millions of liters of liquid ore every hour. The suction force here rivals the engines of a jet aircraft, engineered with fluid dynamics that prevent destructive vortices. The water flows at a meticulously calculated velocity to protect the surrounding ecological balance, even as the pipes swallow enough volume to fill an Olympic pool in mere seconds. Once the water reaches land, it is greeted by massive centrifugal pumps. These turbines, crafted from corrosion-resistant titanium alloys, spin at thousands of rpm to generate enough hydraulic pressure to surge the water to the top of towering treatment spires. Inside the central control room, AI systems monitor every drop. Laser sensors measure flow rates with micrometer precision, ensuring that internal pipe pressure remains constant to prevent a catastrophic hydraulic burst from these titanic forces. The first line of defense is purely mechanical. The water surges through steel meshes, vibrating at ultrasonic frequencies. The goal is to isolate large impurities, sand, and microscopic marine life, as these vibrations ensure the fine pores of the filters never clog. Solid particles larger than a single millimeter are then spun out by centrifugal force. Every grain of sand is a potential enemy to the precision machinery downstream, so this filtration process accepts no errors, operating at a staggering 99.9% efficiency. After mechanical purification, the water enters the silent world of the sedimentation basins. Here, chemistry takes the lead. The water's velocity is slashed, allowing gravity to pull microscopic suspended particles to the floor in a profound silence that precedes the coming storm. Micro-robots inject engineered coagulants and catalysts designed to bind specifically with dissolved metals. We aren't looking for salt, we are hunting for iron ions, hiding between molecules of sodium and chlorine. At the atomic level, the magic happens. The positive charges of the additives attract the negative ions of impurities and heavy metals, forming microscopic gelatinous clumps called floc. This reaction is the cornerstone of separating iron from the rest of the sea. To concentrate the minerals, the pure water must be discarded. The liquid is forced at pressures exceeding 70 bars through semi-permeable membranes, with pores 50,000 times thinner than a human hair. Under this crushing weight, pure water molecules are forced through, leaving behind a thick, hypersaline soup. This concentrated brine, usually considered waste in standard desalination plants, is the crown jewel of our facility. The liquid has now become a dense, high-viscosity brine, carrying dozens of times the concentration of iron and magnesium that was once scattered across the vast ocean. This concentrate enters the heart of the chemical reactors, massive, insulated vats lined with materials that defy extreme acid corrosion. Here, dissolved iron will be coaxed into a solid, tangible form. Oxidizing gases and alkaline agents are pumped in to adjust the pH levels with surgical accuracy. The objective is to hit the exact precipitation point for iron oxide, a delicate chemical balancing act to ensure no unwanted minerals crash the party. Watch as the color shifts. That deep, crimson bloom is the visual proof of iron hydroxide forming. Trillions of solid particles materialize out of thin air, turning the transparent liquid into a thick suspension of raw ore. Meanwhile, giant mixing blades rotate with immense torque but at a snail's pace. The speed is calculated to encourage crystal growth. Spinning too fast would shatter the fragile clusters we are so carefully building. Every minute, a robotic arm snatches a sample, which quality engineers inspect under a scanning electron microscope, or SEM, to ensure the iron crystals have formed the correct geometric structure for maximum purity. Once the reaction is complete, hydraulic valves at the base of the tank snap open. The thick red liquid, heavy with iron, surges toward the most spectacular stage of the engineering process: magnetic separation. This is where the genius of physics takes over. The liquid passes over drums, energized by superconducting magnets, generating a field thousands of times stronger than a common refrigerator magnet. In a scene that defies gravity, iron particles leap from the liquid and cling to the surface of the rotating drum, while water and debris fall away. It is a physical filter that only answers the magnetic call. Hard ceramic blades continuously scrape the drum's surface, gathering a thick layer of iron sludge. This viscous red paste is now concentrated at over 60% iron, the raw material for steel. This metallic dough travels along sprawling conveyor belts, made of specialized synthetic polymers, to resist the brutal environment of salt and moisture. Before moving on, the remaining salt must be purged. The sludge passes under a curtain of pure, fresh water, where high-pressure sprayers wash away harmful salt ions without dislodging the heavy iron particles. Now, the moisture must be driven out. The washed sludge enters massive rotary kilns, giant cylinders stretching 100 meters long. They spin slowly as internal fires roar to evaporate the water, transforming the sludge into a dry powder. Temperatures here hit 300 degrees Celsius. Internal fins toss the mixture continuously, ensuring every molecule feels the heat until the sticky sludge becomes a fine, bone-dry dust. As the powder exits the kiln, advanced dust suppression systems ensure not a single speck of this precious ore is lost. We have successfully moved from liquid seawater to dry, concentrated iron oxide powder. Because dust is difficult to handle in blast furnaces, it must be pelletized. The powder is placed on a tilted rotating disc. With the addition of binding agents and a fine mist of moisture, physics begins to mold the dust into small spheres. Centrifugal force and the angle of the disc cause the dust to snowball into uniform green pellets. This uniformity is vital, ensuring proper airflow and heat distribution in the later stages of smelting. Millions of these red spheres flow like a river toward the thermal hardening stage. Here, they are baked to gain the mechanical strength needed to withstand massive weight without crumbling. The pellets enter a long furnace, exceeding 1,000 degrees Celsius. This heat doesn't melt the iron. Instead, it performs a process called intering, where particles fuse together until the pellets are as hard as rock, yet as porous as a sponge. They emerge glowing with thermal energy, chemically and physically primed for the most violent transformation in the plant: the shift from iron oxide to pure metallic iron. This towering structure is the direct reduction reactor. Here, oxygen will be ripped from the iron pellets, using searingly hot gases in a reverse chemical reaction that restores the iron to its pure metallic state without melting it. Hydrogen and carbon monoxide are pumped from the bottom, climbing through the tower and hungrily reacting with the oxygen inside the pellets. What remains is sponge iron. It has lost its red hue and gained a dark, metallic gray luster. It is now 95% pure iron, though it remains brittle, awaiting its final destiny of melting and shaping. The sponge iron is gathered into colossal baskets and transported by a massive overhead crane. We now stand before the fiery heart of the facility, the electric arc furnace, or EAF, the beast that devours electricity to forge steel. This furnace is a gargantuan crucible, a room-sized beast lined with specialized refractory bricks designed to withstand temperatures that rival the surface of the sun. The lid swings open, and tons of sponge iron are plunged inside in a spectacle that makes the very earth tremble. In that moment, 3 carbon graphite electrodes, each a meter in diameter, descend slowly, like the fingers of a mechanical giant. Through these pillars flows an electrical current surging with hundreds of thousands of amperes. As the electrodes draw near the metal, a massive electric arc leaps across the gap. A roar of thunder erupts through the plant as the air itself is ionized into conductive plasma, and the temperature instantaneously rockets past 1600 degrees Celsius. Under the weight of this hellish energy, the atomic bonds of the solid iron collapse. It transforms into a glowing liquid, boiling like a violent soup as gas bubbles rise and the last remnants of impurities melt away to float upon the surface. At this critical juncture, operators introduce lime and dolomite to form slag. This floating layer acts as a chemical sponge, soaking up lingering impurities like sulfur and phosphorus, while shielding the molten treasure from oxidation. Amidst this chaos, a heat-resistant robot dips a probe into the liquid inferno. The screens flash a reading of 1650 degrees Celsius. A small sample is withdrawn, and its light spectrum is analyzed in mere seconds to verify the precise chemical signature of the alloy. When the steel is finally deemed ready, the massive furnace tilts hydraulically at a sharp angle. The liquid steel pours out like a waterfall of blinding light, casting a glow that overwhelms every other lamp in the factory. The molten metal settles into a massive, refractory-lined ladle. Here, precise alloys, like vanadium or chromium, are added to meet specific demands, granting the steel its final strength and character. A crane then moves, with agonizing precision, carrying hundreds of tons of searing liquid. A single misstep here would be catastrophic, so the entire process is governed by full automation and hypersensitive balance sensors. Before casting, the ladle pauses at a secondary treatment station. Smaller electrodes provide a gentle heat to calibrate the temperature to within a single degree, while argon gas is pumped through to stir the metal, ensuring a perfectly homogeneous mixture. The ladle then reaches the continuous casting tower. The bottom nozzle opens, and the steel flows into a tundish, an intermediate distribution vessel, which evenly feeds the metal into multiple water-cooled copper molds. Inside these copper molds, the outer skin of the steel begins to freeze the moment it touches the chilled walls. The molds oscillate vertically with rhythmic precision to prevent the metal from sticking, allowing it to slide smoothly downward. The steel emerges as a continuous strand, its core still liquid, its skin a glowing, solid red. It is the continuous birth of an infinite pillar of hot metal. Next, the strand enters the secondary cooling chamber. Hundreds of nozzles spray a pressurized water mist directly onto the glowing steel. Dense clouds of steam billow upward as the internal structure of the metal crystallizes and hardens. While the steel is still plastic and pliable from the heat, a series of powerful hydraulic rollers bend the strand, guiding it from a vertical descent to a horizontal path, eventually straightening it into a perfect line. Once the strand reaches the desired length, gas torches move in perfect synchronization with the speed of the steel, severing it with a concentrated flame. Sparks fly violently as long blocks of steel, known as billets, break away, ready for rolling. No energy is wasted here. The billets are transported while still retaining their intense heat directly to the rolling and shaping unit, saving the massive amounts of energy that would otherwise be required for reheating. The billets then enter a gauntlet of massive steel rollers spinning at high speeds. The immense pressure here reshapes the metal, stretching it and reducing its thickness, much like rolling out dough, but with forces measured in thousands of tons. With every pass through narrower rollers, the length of the rod increases and its speed surges. What began as a short, slow block transforms into a long ribbon, racing at the speed of an express train, requiring absolute synchronization between the motors. In the final stage, engraved rollers stamp the distinctive ridges and ribs onto the rebar. These patterns are essential, ensuring the steel grips the concrete in future buildings. The incredibly long rods then slide onto a vast cooling bed where a stepping stone mechanical system moves them inch by inch, allowing the air to cool them slowly and evenly to stabilize their mechanical properties. Once the steel has cooled and settled, giant hydraulic shears cut the rods into standard commercial lengths, 6 or 12 meters, with a sharp metallic crack and millimeter precision. In the adjacent quality lab, random samples are subjected to true torture tests. Hydraulic machines pull the rods until they snap to measure tensile strength, while others bend them to ensure they won't fracture under stress. Under microscopes, scientists examine the atomic arrangement and grain size. A regular crystalline structure is the secret behind the steel's toughness. Any flaw here means the entire batch is rejected and sent back to be remelted. At the end of the line, massive robotic arms gather the rods into neat bundles. Binding machines wrap strong steel wires tightly around them, attaching a tag with a barcode that tells the life story of every rod. Gantry cranes, equipped with powerful electromagnets, lift tons of finished steel with effortless grace, stacking them in vast storage yards to form mountains of shimmering gray metal. What you see here is the culmination of hours of continuous labor, complex chemistry, and raw power. Not long ago, these tons were mere ions dissolved in the salt of the ocean. Today, they are the backbone of skyscrapers. Fleets of trucks arrive to transport this strategic product. Every rod of this steel is destined to build a bridge, a school, or a residential tower, carrying with it the unique story of its birth from the heart of the water. As the sun sets, the work continues in this factory that never sleeps. It is a living, breathing, roaring entity. The floodlights and the orange glow from the furnaces paint a majestic industrial portrait against the night sky. The plumes of white steam rising are not pollution, but pure water vapor from the cooling process. The plant is designed to be environmentally conscious, recycling most of its water and heat in a closed loop. The scene brings us back to the minds that command these mechanical muscles. Engineers monitor the stability of the operations, analyzing data from thousands of sensors to ensure the symphony of production continues without a single sour note. Behind all this technology, the human hand and accumulated expertise remain the decisive elements. These men and women face the heat and the noise daily to turn the dream of extracting minerals from the sea into a tangible reality. From a drop of water in an infinite ocean to a solid pillar carrying immense weight, this journey is a testament to humanity's ability to tame nature and harness the laws of physics and chemistry to build a more sustainable future. We have seen the power of hydraulic pressure, the precision of magnetic separation, the hell of the electric arc, and the art of mechanical shaping. Every stage is a science unto itself, converging to form this superhuman industrial ecosystem. As the sun rises on a new day, the factory continues its tireless labor. The sea does not run dry, and the need for steel never ceases. Here, on the edge between land and water, a new page in the history of industrial engineering is written every day. This is how iron is forged from seawater, a process that seems impossible. Yet, through science and will, the impossible becomes a daily routine.